This is Lab 4 Bar Magnets by Parsa Bahranian. So to introduce this lab, our purpose was to measure distance dependence of the magnetic field due to a small bar magnet using principles of magnetic dipoles. Our system was the bar magnet and the phone. Our surroundings was everything else. A little preview is n equals negative 2.2 and the magnetic dipole moment is 11.6. So these are some of the fundamental principles, physics principles that we use. First would be the Biot-Savart law, which said the magnetic field due to a charged particle is dependent on the particle's speed, charge, and distance from the observation location. Second fundamental principle is magnetic field of a magnetic dipole. A magnetic dipole on a bar magnet is caused by the alignment of magnetic domains within the material. And these are both the formulas that we would have to use. Alright, let's get into the actual experiment. Well, first we orientated the meter stick along the east and west axis to find the correct axis using our magnetometer app. The x component of the Earth's magnetic field was 0 in this case. Second, we found the position where the absolute value of x is maximum and the y component is at its minimum. Third, we rotated the phone by 90 degrees to find the maximum value of the y component and minimum in the absolute of the x component. Fourth, the intersection between these 2 points in the previous steps, in steps 2 and 3, is where the phone's magnetometer sensor lies. So this is about how we got our data. We had to find the distance from the magnet to the sensor that produces a magnetic field with an x component of magnitude 20 microteslas. And then we repeated steps 1 to get 3 measurements, and then out of those three measurements we took an average. And then lastly we repeated the previous steps for 3 other distances of r, and as you can see, this is the data that my team collected on the right. So once we had received all the data, we had to use some mathematical concepts so that we could solve for n, and in this case n was basically our slope, as you can see in our graph that we had created on the right. Once we had this previous information from the other slide that you just saw, we had to find the dipole moment of the bar magnet. Well, from the linearization, we got that n equals negative 2.2 because that was our slope, and therefore ln k equals negative 12.98, which was our intercept. And using this information, we could find that k equals 2.3 times 10 to the negative 6. And these are the following formulas that we use to get to that result. Now we also had to find the magnitude of the off-axis. And we found this by using the bar magnet at a location off the axis of the magnet's dipole moment. This was done by taking multiple measurements to this location of distance and magnetic field, finding the average of these measurements, and then computing the final results. As you can see, it was basically the same thing that we did, just a little bit off of the axis. We found that the magnetic field at a location 0.18 meters off the axis is where the magnetic field would lie. Alright, so this is our GlowScript code, well, a part of it as you can see, and it shows the values calculated in this lab and uses them to create a function that will calculate the magnetic field vectors that you'll see in the next slide. In the images, you can see that we set the perpendicular distance and the magnetic dipole moments equal to the values calculated in the lab. Alright, and this is what we got from our code. You can see the final calculation for the 2 magnetic field vectors on the dipole's axis, the 4 vectors on the perpendicular axes, and the 1 vector at a location and distance away from the dipole at an angle of 45 degrees. The magnetic field at this location is displayed in the output in the text, as you can see in the bottom. So some errors in our lab could be the magnetometer sensors, which were very sensitive and with every movement of the phone, and wires and computers also carry a magnetic field which could skew around the reading that we're receiving. Some assumptions are that the magnet has a perfectly distributed magnetic dipole and the distance is proportional to 1 over r cubed. Alright, so what if we orientated the phone at an angle to the Earth's magnetic field? How would our results change? Well, it'd be a lot different, heavily messed up. This is because the Earth's own magnetic field would interfere with the magnetic dipole, giving us incorrect answers. What if we stick two identical magnets together and run the experiment again? Well, it wouldn't be much different. The only difference would be that theoretically it would be 2 times as strong because we're adding another dipole of the same magnitude to our system. Therefore, all of our results would be twice as great in magnitude.